Okay, let's take a look at 7.3. We've done a lot of Lewis structures, but we're actually going to do that stuff in class because I think it's worth doing those types of things in class. We're going to talk about the Lewis dot symbols. I'm going to do these Lewis dot symbols, and then I'm going to ask that you forget them completely because they are absolutely worthless, in my opinion. So, yeah, so let's just ignore Lewis dot structures after the Lewis dot symbols after we talk about them now. So let's take a look at what we got. So the Lewis symbol is going to be an element, elemental symbol, plus how many valence electrons it has. And so we can actually see lithium is in group 1, 2, 3, 4, 5, 6, 7, 8. So we can see all of these things in different group numbers. And we are going to fill them according to how many valence electrons they have. So lithium, easy enough. I'm going to put the valence electron there. It doesn't matter. I could have put it on any of the 4 sides. There are 4 sides. Electrons can go anywhere they want. Okay. All right. So lithium, that's where the electron goes. Beryllium, 1 electron. There's my 2nd electron. Okay. Boron, 1, 2, 3. Carbon, 1, 2, 3. By the way, 4. There's my 4th electron. By the way, S, and there are my p orbitals. We generally, when we're kind of looking at doing it this way, this is an organic thing, we end up with combining these things together. And S and 3 Ps, we're going to call this sp3. So I'm going to combine those together. And so the first, if this are carbon, 1, 2, 3, 4 electrons go there, right? So if I put the next electron in, where is it going to go for nitrogen? It would go there, right? So that's going to pair up. And in fact, that's what we're going to see when we represent that. So nitrogen is going to get 3, 4, and then the 5th one is just going to pair up. Okay, so that's kind of where this all comes from. In fact, I can kind of ignore calling this carbon because that's ultimately that red one right here is the one that we're talking about for nitrogen. And I'm going to pause here because nitrogen is a good demonstration of this. And actually, I'll do it for oxygen. So oxygen is going to have 1, 2, 3, 4. Again, technically how we do it, individual, and then we're going to fill up. It doesn't matter which side we do it on. They're all degenerate. They all should be equal energy. So with that said, when we have oxygen here, a lone pair is 2 electrons. We would also call this a, let's see here. Let's see if I have space for this. Yeah, so this is going to be called a lone pair. I really hate doing it this way, but I know I'm supposed to show it. It's annoying. All right, sorry, that's a lone pair, or what we'd actually call this is a non-bonding pair. And that is the same thing here. So this is the lone pair. That's the lone pair of electrons. Because it's 2 electrons kind of in their own little shell, like they don't want to pair, they don't want to bond. This right here, on the other hand, I'll use a different color for this. Sure. There you go. That right there is going to be a bonding electron, because, and this is an example of a bonding electron. Those 3 are examples of bonding electron. It's one, it's just waiting for another one to create a bond with, because we need 2 electrons for a bond. So that's a bonding electron. So it's ready to create a bond. So how many bonds do I expect carbon to form? It's got 4 bonding electrons. I expect 4 bonds, and that's it. Nitrogen, I expect 3 bonds and 1 lone pair. Oxygen, I expect 2 bonds and 2 lone pairs. Fluorine, and now I can just skip ahead. 1 bond, 3 lone pairs, and neon is going to have a full shell. So I'm going to do this, and it's going to seem easy to do it this way, but this is not the way to do it. Again, the octet rule, we should gain 8 electrons. Again, you can get rid of electrons until you go down to 0, right? Because that would take you to the previous noble gas, or gain electrons until you get to 8. Again, we ignore the D. We're typically talking about the S and the P electrons together when we're talking about the octet rule. So forming compounds, formulas using Lewis symbols. This is what I want you to forget. So if I have sodium with 1 electron and chlorine with 1, 2, 3, 4, 5, 6, 7 electrons, these two things are going to combine together and it's going to create a bond. So now I have sodium with a bond to chlorine. But that's not in fact what happens, because what ends up really happening is sodium is going to just transfer that electron. And so what you should end up with is sodium plus and chlorine minus. How do I know? The delta En, the change in electronegativity. Okay. And so that's kind of, well, one of the problems with this, but again, that whole idea of what kind of compound would we make out of these things? Form 1, 2. Ultimately, what this leads to is I don't really care if it's bonding, if it's covalent or ionic. What this is going to make is K2S, 2 potassiums for every sulfur. This is a 1-to-1 thing, 1 sodium and 1 chloride. What do we expect aluminum and fluoride to get? Spoiler, AlF3. Again, I want to get over this because I don't think this is a useful tool. So single sharing covalent bonds. So same thing. If I have fluorine combining with another fluorine, let's create a bond. We've got one bond. They both have 1 bonding electron, and we can create a bond between those two. And we now have F2. Yay, we did it. Fantastic. What about H with F? Create a bond. In fact, don't. What you end up with is HF. Again, I think this is useless. What's the compound you expect to form between S and Cl? Both nonmetals, so we know that we're going to form bonds. Again, I want you to see this so you can understand it, but I want you to immediately forget it, because what ends up happening is as things get more complex, as they typically do, you end up in a situation where you're going to get it wrong if you try to do it this way. So this is a poor exercise. But anyway, I'll let you do those two, and maybe we'll talk about them, but we'll probably skip over them anyway. Same concept here. An oxygen has 1, 2, 3, 4, 5, 6, and the other oxygen does as well, creating a bond out of these two. So we expect 1, 2 bonds to form, creating, and there are a number of problems with this one, but there we go, we've made our structure. Okay, do the same thing for CO2 and try for nitrogen, and you're going to see that you would form a triple bond. Drawing of Lewis structures. Again, count the valence electrons, because we've talked about this before. Let's talk about it again, I guess, in some detail. We're going to count valence electrons. We're going to write the skeletal structure, which just simply means 1 electron to each one. And we're always going to use the center atom as the least electronegative or most electropositive, the one that's furthest from fluorine. We're going to satisfy the octet of the periphery. Then we're going to add any leftover electrons in the center, and then we're going to multiple bond if we need to. So we're always going to follow these rules. And so I'm going to walk through the first, I'll walk through the first 2, or I'll walk through the first one. No, this is the one I'm going to walk through. I'm going to walk through, screw it. I'm going to walk through NF3 here. So nitrogen has 5 electrons. Fluorine, there are 3 of them, times 7. Okay, so you should have, what's that, 14, 21, so 26 electrons. Okay, so I'm going to create a skeleton. The central atom, by the way, nitrogen is less electronegative, so it's going to go in the center versus fluorine. But generally, nitrogen is the center of this one. What do you think is in the center of this? It's carbon. What do you think is in the center of this? It's carbon, because carbon is always a central atom. But the first thing that's kind of isolated on its own tends to be the center atom. Nitrogen here, sulfur here, chlorine here. So we typically just go with what the lone atom is. That's another good way of doing it. So going back to this. So I just created 1, 2, 3 bonds. That is 6 electrons. So I've gotten rid of 6 electrons. I have 20 electrons left. So now I'm going to step 3, which is satisfy the octet of the periphery. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I use all 4 sides. So this fluorine has 1, 2, 3, 4 sides and 8 electrons. A bond counts as 2. So I just did, was it 6, 10, 6, 12, 18. I just did 18 electrons. I have 2 electrons left, and I'm going to add the remaining electrons to the center atom. And then finally, I'm going to check, is nitrogen happy? Does it have 8 electrons? It does. This thing is in fact correct, and we're good to go. So try CO2s, try CH2O, and we're going to do a bunch of examples in class. Polyatomic ions, I'm just going to do the counts, and then you can do these. Nitrogen has 5. There are 4 hydrogens at 1 each. And this positive charge indicates that we lost an electron. So that means that down here, I'm going to minus 1 electron. So you should have 8 electrons for this structure. SO4 2 minus, sulfur has 6. Plus the oxygen, there are 4 of them for 6. Okay, not equals yet. This 2 minus indicates that I have gained 2 electrons. So 2 plus 2. Right, so 32 total electrons we should have here, okay, and so on and so forth. So just make sure you always check for that charge. So we'll take a look at these, and we're going to do some more complicated ones, but yeah, it's definitely worth a look. Please ask me in class if you have any questions. I know I like breeze through this because we've done those structures. And I think it's important to know how to do this. The dot structures are pointless, and I will die on that hill.